Now, for a convex mirror, let me draw this again. All right. Now, let's say this is a convex mirror. So we're looking at the outer surface here. We've got, if we have a bunch of parallel light rays coming in and hitting the mirror, following the law of reflection, they're going to bounce back in all directions, but they're going to be bouncing back so that their angle of incidence and angle of reflection are equal. And I'm just estimating where these are going to be. But for an actual mirror, and looks like I've drawn this reasonably well, if you kind of extend these lines backward, all of them will converge on a single point. Now in my drawing they haven't quite done that, but you get the idea. I don't know if I had drawn it perfectly, then they would have, and it's actually is what happens. There's this point back here where if you extend the rays backwards, they would all converge, and this is called the focal point of the mirror. Right? For a concave mirror, all these rays come in, and you don't have to extend them back, but they all do just reflect in toward the focal point of the mirror. They would all converge at that point. Okay, and that point, yeah. So for a concave, the rays actually converge at that point. For a convex, to extend the rays backward, they would converge at that point, and because extending them back, they would converge at that point. It looks as though that point is the source of the rays. Okay, and for both of these, the focal length for both kinds of mirrors, and it'll turn out for lenses, which we'll talk about later, the focal length of the mirror is an important property. The focal length is the distance from that focal point, or it's also referred to as the focus, which is slightly shorter than saying focal point all the time, to the mirror, but that's along the principal axis. So it's not just any distance to the mirror, but it's right here. And the distance to the mirror in any direction is not the same because this is not the center of curvature of the mirror. But it turns out, however, that there is a way to determine exactly where the focal point is. So the argument goes like this. We've got a horizontal incoming ray has some angle of incidence. It reflects off, and this is our axis. It's running from the center to the point of contact. And this angle is, these two angles are equal by the law of reflection. Now if we draw this little triangle in here, this angle is a vertex angle with this one, so those two are equal. Now FC here and the incoming ray are both horizontal, and this is the same line for both triangles, which means that this angle is also equal. So that tells us that if I call this point A, that tells us that FC is equal to FA. Those two are equal to each other. And here's where we make a bit of an approximation. If we say that these angles are small, then we can say that AC is approximately the sum of those two sides. As this angle gets really small, that triangle will become closer and closer to where these two sides add up to that line. And so that's the approximation we're making. So because we're using that approximation, there's something that we're assuming. We're assuming that this is a small enough section of a sphere that the surface is only curved a tiny bit. So if we've got a spherical thing, we're looking at stuff that's happening in a very localized region. If I worry about light that's coming in and hitting, say, a hemisphere of a plane mirror, then this approximation breaks down. So based on this approximation, then we can say that our focal length is equal to half the radius of curvature of our mirror. So for a convex mirror, we say that our focal length, we actually say it's minus 1/2 times the radius of curvature. For a concave mirror, we say that it's positive 1/2 times the radius of curvature. This minus means that it's a distance behind the mirror. The convex mirror has the focal point behind the mirror, while the concave mirror has the focal point in front of the mirror. And that's why how we assign those positives and negatives. Okay, and this is for small angles, so they don't quite converge as you go further out. And so this is known, it's called a spherical aberration, that for a circular, or for a spherical lens, as you get further and further from the principal axis, images that are reflected get more and more distorted and blurry because of spherical aberration in the lens, right? Because of this approximation we're making that these angles are very small. So the focus, the rays don't all quite converge at the focus if you get too far away from that principal axis. Now we can fix that. A parabolic lens, if the lens is a parabola, then the rays all do converge at the focus regardless of how far they are from a principal axis. So that can take care of the spherical aberration, which is a principle that's used in telescopes to create sharper images. Also, if you put a source at the focal point, you can kind of run this in reverse. And if you've got a parabola, you put a source of light at the focal point, the light will bounce off in all directions, and then the rays will come out all parallel, following the law of reflection. And that's used in things like headlights and flashlights and things of that nature.